Many management failures stem from a single, specific flaw in planning, relying on deterministic estimates to predict future outcomes. Deterministic approaches operate on the assumption that a future value can be known with absolute certainty. You set a target, draw a straight line, and expect reality to comply. The actual market does not behave this way. It is governed by overlapping probabilities, fluid variables, and entirely unpredictable external events. To establish rigorous financial control over operations, managers must discard rigid predictions and adopt probabilistic modeling. The primary tool within this framework is expected value. This is a calculation that associates a specific dollar amount with each possible outcome of a probability distribution. Abandoning the illusion of absolute certainty is the mandatory first step to gaining true operational control over your risk. We resolve this probabilistic tension using a visual framework known as the payoff matrix. The vertical axis typically maps decision alternatives. These are the specific choices entirely under the manager's direct control. The horizontal axis tracks the states of nature. These are the future events the manager is attempting to predict but cannot control. The exact intersection of a manager's decision and the actual realized state of nature creates the financial result, known as the payoff. There is one absolute rule for constructing this matrix. It must be totally exhaustive. Every single variable, from unsold inventory scrap rates to hidden storage costs, must be captured in the raw data. Failing to account for these specific secondary factors corrupts the internal logic of the entire analytical framework. This is a payoff table analyzing the inventory options for a luxury yacht dealer deciding what to stock for the upcoming season. We first isolate the manager's available decision levers. They can choose to order 0, 1, or 2 yachts. Next, we map the states of nature. Projections suggest a 10% probability of 0 demand, 50% probability for 1 yacht, and 40% probability for 2. The financial payoffs dictate a clean $200,000 gain for every unit successfully sold. However, there is a critical hidden risk built into the cost structure. A $50,000 carrying cost penalty applies to every single piece of unsold excess inventory. Looking at this matrix, a risk-averse manager scanning the bottom left corner sees a potential $100,000 loss. Emotionally, they might reject the maximum order of 2 yachts entirely out of fear. We calculate the expected value for stock 2 yachts to evaluate this decision scientifically, bypassing visceral bias. We do this by multiplying each potential payoff in that row by the corresponding probability of that specific state of nature occurring. Summing those products yields a final expected value of exactly $225,000. The math dictates that stocking 2 yachts yields the highest expected monetary value. The optimal choice is clear: stripping the emotional fear out of the boardroom. This introduces a new strategic question. What if the manager wants to hire outside analysts to completely eliminate this market risk? This requires modeling perfect information, the absolute certain knowledge of exactly which state of nature will occur before the decision is made. This new table demonstrates the calculation for expected value with perfect information, known as EVPI. With perfect foresight, the logic of the matrix shifts. The dealer's inventory decisions now map exactly 1-to-1 with actual demand. They will never order excess stock, neutralizing the $50,000 carrying penalty completely. Under these flawless conditions, the new calculated total expected value rises to $260,000. To find the true worth of this data, we calculate the delta. We subtract the original baseline expected value of $225,000 from this new perfect scenario. The EVPI is exactly $35,000. This number isolates the maximum additional financial gain available when market uncertainty is entirely eliminated. Therefore, $35,000 is the hard ceiling the firm should ever pay for market research. Spending $35,000 and $1 objectively destroys value. We must now challenge the bedrock of our baseline model. The initial demand probabilities of 10, 50, and 40% were highly subjective estimates. To evaluate how prediction errors in those estimates might impact the optimum solution, we utilize sensitivity analysis. The objective here isn't to magically find perfect numbers. The goal is to locate the exact threshold where the optimal decision actually changes. This series of tables compares the original probabilities on the left against 2 radical new alternative distributions. We analyze the first alternative, testing a drastic shift, a 50% probability of zero market demand. While the overall expected dollar value plummets in this scenario, stocking 2 yachts mathematically remains the superior choice among the 3 options. Next, we test the second alternative, a completely flat, perfectly even probability spread of 33. Sensitivity analysis proves that managers frequently overpay for precise data. If you know with confidence that demand will not hit that 80% threshold, expending further resources on a better forecast is completely unjustified. We have established 3 definitive pillars: the baseline optimum at $225,000, the strict intelligence ceiling at $35,000, and the operational flip point at 80% demand. Expected value analysis takes variables that would otherwise be left to intuition and guesswork and subjects them to scientific management techniques. Its true value is procedural. It forces leadership to evaluate all possible states of nature and map every hidden cost in a highly organized manner. Analytical rigor functions by defining the precise mathematical boundaries of risk, rather than attempting to predict the future. We must conclude by addressing the fundamental paradox of expected value models. The mathematics of expected value are predicated entirely on repetitive, infinite trials to normalize probabilities over time. However, in reality, most high-stakes corporate finance decisions are single-trial events. You only get to build the factory once. No probability model can guarantee success on one isolated, unrepeatable attempt. Choosing the highest expected value does not eliminate the possibility of the worst-case scenario actually coming to pass. The payoff matrix cannot dictate reality, but it does provide a mathematical guarantee that, given the available data, your decision-making architecture was the most rigorous, defensible option possible.